All right, so we're going to be looking at the concept. This is actually one of the more important applications of derivatives, which is to look for maximum and minimum values of a function. And so we're really going to lay the foundation for this concept, and we're going to explore this in more detail as the chapter progresses. All right, so first we're just going to define this. So if you have C, some number in the domain of D of some function f, we say f of C is the absolute maximum value of f on this domain D if the function value at C, f of C, is greater than or equal to f of x for all other values of x in the domain. Basically, nowhere in the domain can you attain a higher value than f of C. Then it's the absolute maximum value of the function. By the same token, C would be the absolute minimum value of the function f if f of C is the lowest possible value of the function, right? I mean, that's what it means. Absolute maximum, absolute minimum. And we can use, sometimes we substitute the word global for the word absolute. So we might refer to these as the global maximum or the global minimum. All right, so now the idea of local extrema. F of C would be called a local maximum value of f if the function value at C, f of C, is greater than or equal to f of x for all x's that are near C. Not necessarily for all values on the entire domain, but just near C. This is locally a maximum. So when we say near, we mean if you can define an open interval to the left and to the right of C for all values of x in there, f of C is the greatest possible value, then it's a local maximum of f. It's a local minimum if f of C is less than or equal to f of x for all x near. So you should have in mind the idea that like a local valley or a local hill, but it may not be the highest altitude or the lowest altitude everywhere on the domain. It's just locally it is. It's like a little dip or a little bump. Technically, an absolute maximum value is also a local maximum value, but doesn't work the other way. Okay, so first example, take the function f of x is the cosine of x. So you can see that just looking at the graph that we do have these minimum and maximums occurring, right? We would say that well, you know already that the cosine oscillates between -1 and 1, so it's clear that 1 is the local max value. Actually, we can say that 1 is the absolute maximum value. -1 is the absolute minimum value. And now it doesn't mean that it only occurs in one place. You can see that the value 1 is going to occur an infinite number of times at every time this oscillation occurs. But that's the highest value of the function. You could never get a value cosine of x greater than 1. So that's the absolute maximum value. Okay, that's just the concept. Okay, so take the function f of x is x squared, a parabola, right? You know, just looking at it, you can see that the lowest value that this function takes is 0. So you can have 0 is the absolute minimum value, but there's no absolute maximum, right? Because this function increases unbounded in both directions. So this is a function where there's an absolute minimum value, but there is no absolute maximum value. In fact, there's no local maximum values either. Anywhere on the curve, you couldn't create an open interval where that function value is the highest in that open interval, because it's always going to be increasing to the left or it's increasing to the right, depending on where you're at. If you're over on the left-hand side of the vertex or the right-hand side of the vertex. Okay, so if you take the cubic function, you can see here actually that because this function, it's always increasing. there's no one value that's an absolute maximum or an absolute minimum value. There's neither. In fact, the only place that you might think that you might find something here, it levels off, but that's not a local minimum or a local maximum, because slightly to the left, it's always going to be less, and slightly to the right, it's always going to be more. So there's no absolute maximums or minimums. There's no local either. So there's no extrema of this graph at all on the entire domain of the real numbers. Okay, so let's take a look at this this function, 3x to the fourth minus 16x to the third plus 18x squared. It's this polynomial. You notice that it has this shape where you do have these local minimums and local maximums, or this one local maximum. And it seems like at this point here, we can plot this point, and it turns out that when well, this is the point 0, 0, right? This other extremum is, so you plot these points. You actually have three. You could work this out by zooming in and see clearly that these are the three local extrema. There's at the point 0, 0. I should say that this is the point at 1, 5, and then we have over at 3, negative 27. So what we have here is we do have a local minimum value of 0 that occurs. We have a local max value of 5. We have an absolute minimum value of negative 27, but on the entire domain of all real numbers, there's no absolute maximum value, because this polynomial increases unboundedly to the right and to the left. So there's this theorem, if you're not looking at the entire domain of the function, but rather you're looking at a closed interval, as long as the function is continuous on a closed interval from a to b, then the function must attain an absolute maximum value f of c and an absolute minimum value f of d at some c and d on this interval, right? If your function is only if you're looking at from a to b, no matter what your function does, as long as it's continuous, it must get to some lowest point and it must have some highest value, no matter what crazy curves, because it's always going to have a range of values as long as the function is continuous. The only way that this thing wouldn't, if this thing goes up to infinity, but if it does, then it's not continuous on the interval, because infinity is not a value. You couldn't go all the way up to infinity and still be a continuous function on the entire interval. That wouldn't work. Okay, so here's an important theorem, and this is going to be the basis of a lot of the other stuff that we're doing. Fermat's theorem, it's not Fermat's last theorem if you've heard of that. This is just one of his theorems. If your function has a local extremum, which is to say either a local maximum or a local minimum at c, and if the derivative exists at c, then the derivative at c has to be 0. It can't be anything else. As long as, but if the derivative doesn't exist, then well, it doesn't equal 0. So as long as the function is like is a smooth curve at c, then it must be leveling off. It must have a zero derivative there. That's the only possibility at local extremums. That doesn't necessarily mean if the derivative equals 0, it doesn't necessarily mean you have a local max or local minimum. But this is one way we can try to find them, find the local maximums and local minimums. So any value c in the domain of f, such where either the derivative at c is 0 or the derivative at c doesn't exist, we call those numbers in the domain critical numbers. Might call them critical points. So we're going to be looking for critical points and as candidates for a possible local extremum. Okay, so take this function. F of x is x to the 3/5 times 4 minus x. We want to look for all the critical numbers for this function. And so we're going to take the derivative. we're going to have to use product rule. So it's going to be 3/5 times x to the negative 2/5, 4 minus x, plus x to the 3/5 times the derivative of 4 minus x, which is a negative 1. Okay, so let's actually let's factor this because you can see that you've got x. Let's see what we can factor out. Let's factor out an x to the 3/5 and see what this looks like. So we're going to have 3/5 x to the negative 1 minus 1. And this, let's write this x to the 3/5. Actually, let's take, and then we have 3 times 4 minus x over 5x minus 1. What I'm going to do is actually take this, right, x to the 3/5. This is going to be 3 times 4 is 12 minus 3x over 5x. I'm going to subtract 5x over 5x. And so that's actually going to be x to the 3/5 times, this is going to be 12 minus, it's 12 minus 8x over 5x. Okay, so when would the derivative be 0? If x equals, let's see, if this numerator here is 0, that could happen. That would be 12/8, 12 over 8, which is 4, which is 3 over 3/2, right? Or when x equals 0, something funny is happening. Well, certainly it looks like we're getting a 0 for this, but you notice we have divided by 5x. So either this is going to be, this derivative is not going to exist because you can't divide by 0, right? So these are both the critical numbers for this function because the derivative is either 0 or it doesn't exist for these x values. So then this leads to this method that we use to find the absolute max and minimum values of a function on a closed interval, called the closed interval method. So basically what you do, right, you have to find all the critical numbers and evaluate the function at all those critical numbers. So you find the function value at every critical number. You then find the value of the function at the two endpoints, and then you just compare them. Which of those values is the largest? Which of them is the smallest? Then you're going to have your absolute maximum and absolute minimum values of the function. Here's an example. Okay, let's consider this polynomial x to the third minus 3x squared plus 1 on the interval -1/2 to 4. So what we're going to do is find the critical values. F prime, it's 3x squared minus 6x plus 0. So this is actually, I'm going to factor this. I'm going to factor out 3x, and what I'm going to have left is x minus 2. So you can see that you have your critical numbers are 0 and 2. And so you evaluate them all. You evaluate f of 0, all right, and that's going to be 1. And f of 2 is, let's see, 2, that's 8, minus 3 times 4, it's a 12, plus 1, so 8, 9 minus, that's going to be -3. And then you're going to also evaluate the endpoints, f of -1/2, sorry, -1/2, and just working that out. This comes out to 1/8, just trust me on that, and f of 4. Also, just trust me that when I say this comes out to 17. So after you do all that, we then just compare them. And you can see this is the absolute minimum value, and this is the absolute max value. That's the idea. Although, f of 0 is 1, well, that's not the maximum value on this entire interval. And so that's the idea of using the critical points to find absolute maximum and minimum values. And what we're going to do a little later on is to actually try to classify what kind of a extremum it is, if it is at all, what kind of critical value or critical point, critical number, whatever you want to call it. But that'll be in the next section we'll be looking at. All right, bye.